Hi, welcome back. So we are in chapter 3. You must know add the outline of a mathematical constant number and its natural logarithm, the ln. So first of all, I'm going to remind you the difference any polynomial number and raise it to a certain constant of power, right? For example, the case of x raised to the power of 2 or x raised to the power of 3. If we make the base to be constant instead of the power and raise it to indeterminate value of x, for example, you could take base of 2 and raise it to x, or maybe base of 3 and raise it to x, and so on and so forth, and take you back to understand the meaning of slope. Why we are striving when we have such an equation in quadratic form or cubic form or in any power to reduce it down to the point where we need a function looks like linear to us. If we would have such a quadratic form, for example, we cannot get such a line. Look at each point on this line and we discovered that each point has its own line. I'm going to introduce you to two important tasks. First of all, we will visit this one more time by observing these slopes are approaching the value of 1. This is the first task. And the next task I would like to do actually is to study not only the slope's behavior, but also the function behavior. I mean, those values of y. Now, in the previous section, I've shown you this code. Y calculated the y, and that is the value of y to the power that we are deciding here, power of 2, for example. We're going to change it to 3, whatsoever power you like. So let's get the result as you expect here. So at input of 1, we got 1, input of 2, we got 4, 3, 9, and so on and so forth. Look at the slope at this coordinate one more time. It is 2, and next slope 4, 6, 8. So it is automatically easy to observe each slope was increasing by 2, which is actually the constant power. That's why it was increasing by 2. Just let me go to the last coordinate. I get the value of 99. I get y to be 9,801. And the slope in this case was 198. Now what we're going to do, we're going to take each current slope and compare it as a ratio to the previous slope and see what we will get. So in the first case, now my current slope is 4, the previous was 2, and the ratio between them it's 2, which is 4 over 2. My current slope is 6, the previous is 4, which is just now was current, and the ratio between them is 1.5. So if we go all the list down, we could see the last slope when it was 198, the previous 196, the ratio between them, it got almost close to 1, not completely, indicating that the line is getting steeper and steeper. And what does that mean? I mean, this point of getting the slope is getting steeper and steeper. To find out that, I would like to investigate from the perspective of the y. Now, the current value of the function, it is 4. The previous was 1. Now, the difference between them, I mean, this current point and the previous one is 3. A 3 is a 300% of the previous value, 75% of the current value. Then, the difference between is 5. And 5 is actually 125% of 4, and it is 55.56% of 9. Let's go ahead until the end. And this ratio in comparison to the previous and the current, you see, is only 2%. So we started with a 300% difference between the two values. It went all the way down to become only 2%, the difference between them. What does that tell us? As I proceed with this function power of 2, the grow is going to the power of 2. At some point, which we actually get x only 100, the power of this power, it get lost somehow to affect the difference on the value of the y. Now, if you change this to any power you like, for example, let me get power of 3. So the difference between them, look here, was 700% until we reach only a 3%. So I hope this visual presentation on numerical reading is quite clear to you. Now, these 2 points, I hope they are clear. I want to ask an important question. Why do we care get these slopes of the line? So we got this function here, and we should be familiar with it. Minus x squared plus 5 of x plus 2. And once again, let's discuss the question is, we need slopes of lines on each of these points. So what we got here, we got value of 0, 2. The slope of this point is 5. This is the slope of the first line, all right? The second slope of the point 0.5, 4.25, the slope is 4, tangent, right, at this particular point. Somewhere along these slopes, I will get a slope of 0. And what does that mean, slope of 0? Means at this point, at 2.5, 8.25, and that is the maxima. Another example of a minima. You will see that somewhere along the line, you see at the value x is equal to 2 and y is equal to 4, the slope was 0. Means at this point here. So we want to move farther to the second case where we could have a constant to an indeterminate power of x. This is what we call y is equal to c to the power of x. Now let's try to understand this function first and see some characteristic that differentiated from the case of having the base to be indeterminate. This function, it seems to be intercepted at the value 1. Let me here create some point. So these are the point that we have, and we would like to create a kind of intercept line for each point as we just done before, right? If you remember in the first case when our base was indeterminate and the power was constant, we started with slope like say 2 and then 4 and then 6 and then 8. Now, I would like actually to record the case in a reverse order, like 2 to the power of x. Let's try to find what are the slopes here. Let's go ahead and try to print the coordinate and find the slopes. Now, we get the first point, which is 2 to the power of 0 is 1. 2 to the power of 1 is 2, and so on and so forth. So this is the slope, which is 0.6931, then 1.386, then we got 2.772, etc. Now I want you to see, do you see any pattern here when we have the base to be indeterminate and the power to be constant? You will see that the slope was actually arithmetically moving. So it was just only +2. However, in this case was geometrically multiplied by the base of 2. Matter of fact, let's go ahead. This is the value. Multiply by 2. You will get 1.386. And again, multiply by 2. 2.7. Multiply by 2 and go on that way. So you get 5.54. So this is a very important observation you have to keep in mind. That if our function, the base is indeterminate, the slope is arithmetically increasing. However, if the base is constant, slopes geometrically are increasing. So in the case of this one, when we have a constant power of x, what I need actually, I need this essential value to be considered like my first alpha. Just like in this case, I have 2 was my considered alpha. I'm getting back to the example here. Getting this, and I want to show you you shouldn't be surprised. So this is my previous or the essential slope, and then I just multiply by 2, I get this one. Now multiply by 2, you get this one. Multiply by 2. So the ratio between them, it's equal to that base. Now, the next thing I would like to do actually, take the difference between the current and the previous value, and we take that ratio and compare how much percentage from the values of the y. So in this case, what's going on here? We got the first value happens to be 1, which is 2 to the power of 0 was 1. And the current value now is 2 to the power of 1 is 2. So we got the previous value was 1, now is 2. The difference between them is 1. So you could see 1 is 100% of 1 and is 50% of 2. How about the second 2 value of y? So it is 2 and 4. The difference is 2. Once again, it is 100% of the first value, 50% of the second value. Wherever this function grows, the difference stays constant, is not going to change. And why? Because my base is constant. In our previous example, when we have the base indeterminate, we saw that idea was different. Now we have x power of 2. See 300% and went down to 70%, and until it became the difference between them smaller enough to be negligible. Unlike when we have the base, in this case, you see, it will always be constant. I hope that this image, it makes quite a sense to you. Now let me get back to my example here and start with a ratio. As I said, the first ratio of 0.693 1. Slope that we need to get around this point here, and from here you start to multiply the slope by 2, and then this line is gonna get steeper and steeper and steeper. I think the idea is in there. All right, let's change now the base to be 3. Okay, so when we got 3, look at the slope now has changed to 1.0986. So it isn't exactly 1, but can we get a number, a base, let me say, that if I find the slope of the line to be exactly 1, why is that important? Because when you start to understand the derivative in a while, if this happens to be the alpha, the first value is always 1, that means every and each slope followed by that, it will be exactly identical to the value of the y. I mean, it will be the function itself. And that is where the number e was introduced. This is the value of e, which is equal to 2.7182. This irrational number goes on and on without any repetitive pattern. That's how if we take a base of 2 and then we take base of a 3, we saw actually the difference through the investigation of the slope. Now, let me get to write here exactly the value of e. So these are the values where we got 0 and 1, and watch carefully what is the slope of this equation. It is exactly 1. It means it's exactly equal. Whatever the value of y, that is my slope. Whatever the value of y in the second case, that is my slope. Let's see what's going on and see the difference between them. Of course, this is my function where the e is just between the both of them. This is my first slope line. And here we go, you got slope the second line and so on. So you could see that the slope for any point in this line is exactly, the slope of this line is exactly equal to the value of y. The next thing I would like to show you before we close down on this section, actually, it is related to the ratio difference. The difference between this and the previous value of y, it is 171%. And from the second value, it is 63.21%. That always will be 171.82% of the first value, 63.21% of the second value. So next, what we're going to do actually, we are going now to take one step further by investigating the power of E as a constant number from, for example, in the field of finance. That's exactly what we're going to do next. I'll see you then.